As you said, it's about constructing and predicting school advice for academic achievement, a comparison of item response theory and machine learning. First of all, thank you all for being here, whether it's morning or in the afternoon. So let's get started. All right. So let's start with a brief motivation of why we did this study, followed by a data background, so where we got the data from. Next, we'll discuss some of the analyses that we did, the methods, the comparison between item response theory and machine learning. Before we move on to the results and the conclusions, and we end with a discussion of what we found and a theoretical explainability of evaluation, which will be important, as I will say later on. So first of all, the motivation of the study. So I assume most people are not familiar with the Dutch education system. More specifically, the secondary education system in the Netherlands is characterized by division. As you can see in this figure, the red blocks are for secondary education. There are roughly 3 major school types. And as the arrows indicate, you can switch between these school types. You can actually also go the other way, as is actually not indicated, but you can. And usually switching between these school types occurs in the first 3 years. In our data, 19% of all students made a switch. And that is problematic, since what you really want is to get into the best or the most suitable school type right away, since your school type determines tertiary education and your job perspective, since from there you can move on to either an applied university or a research university. As you can see here, it ranges from more vocational to more academic. But this of course also raises the question, which school type is most suitable for a particular student? So what we want to do is we want to give school advice to students as to where they want to go to, where the advice is simply the actual school type in year 3. So we will look at the first 3 years. At the moment, teachers also give school advice to students, and they do that based on just how well they know their student, but also based on their grades. And their grades are based on a series of tests, and these tests aim to estimate knowledge on a specific content area, such as Dutch, English, mathematics. And there's a special interest in those who switch school types. So we have to make sure that we don't leave out this group. Otherwise, we could simply predict that no one switches, and then we have an accuracy of 81%, since 19% switches. So the question we ask is, how can educational tests be used to predict school advice? So we give the school advice, but we really predict their school type. That's how we refer to it. So a brief description of the data background. It's an already existing data set consisting of nearly 18,000 students, spread over all 3 school types. They have been administered tests at 4 different measurement moments. A measurement moment, so there are 4, one at the beginning of year 1, one at the end of year 1, and at the end of year 2 and 3. And per measurement moment, there are also multiple test versions, 4 to 5, depending on which measurement moment. And these test versions are necessary to accommodate the different school types, because otherwise it wouldn't be fair to give a very difficult test to someone at the most vocational school type, or a very simple test to someone at the most academic school type. On average, there are about 290 to 360 items per test, which leaves us with just a bit more than 5,000 administered items in total. And all items are on the content areas of Dutch, English, arithmetic, and mathematics. So there are different parts of the test with different items for these content areas, but we see them as one test. So a bit more about the school advice. So that is really the outcome variable that we want to predict. For my fellow countrymen will know that there are actually more than these three major school types, and there are also subtypes, but we have aggregated these to present the major types. And in this figure you can see the distribution of students. So you see that most students are in the most more vocational type, and there are fewer in the most academic type. And as I said before, 19% of students switched school types, of which 58% went upstream, so that means so more academic type, and 42% downstream, so to a more vocational type. So switching does occur in both directions. It's a bit more to more academic type. So about the analyses, about the comparison between item response theory and machine learning, which is what the paper is about. So first of all, item response theory, I assume most people here are familiar with it, but it's a popular method in test theory where we want to find the ability of students, where the the ability, what we really want to do is to make an ordering of students ranging from the best to the worst score, and we call this an ability. It's a latent trait. So we calibrated a rational model on a unidimensional scale. We have also tried to do multidimensional item response theory, but that didn't really work out because of some problems with the data. So we kept it simple with a rational model. And then we extracted this ability using expected a posteriori. But of course, we don't want to find the ability, we want to predict their school advice. So we plug these ability estimates into a multinomial log linear regression to predict the school advice at the end of year 3 from the ability at the start of year 1. And then you get these nice curves in this, as you can see in this figure, where you can draw cutoff lines so that someone with an ability of less than 0.82 will be classified as in the most vocational type. Someone with an ability higher than 1.38 gets classified as belonging in the most academic type, and in between is the middle type. You can see that it's sort of being squashed in between the other types. That is also something you see in the performance measures. So we did RSC analysis, and there you can see that the most vocational and the most academic type have about the same performance over all thresholds, whereas the Halvo middle type performs much worse. But overall, we find that to be a sensitivity of 0.66, a specificity of 0.83, and an average area under the curve of 0.826. So that seems to be quite good, but of course that also depends on the thing that we want to compare it with, which is machine learning. So we have looked at two different methods. We looked at a random forest and a neural network. These were chosen based on their complexity, where a random forest is less flexible or more robust, so less complex, whereas of course a neural network with its hidden layer, it's more complex more flexible. And we hypothesize that a more flexible method will do better for the students who switched, whereas a more robust model would do better overall. One problem was that we had a sparse matrix that was due to the data collection design with the different test versions per school type. So there are a lot of items that students were not administered because they were for a different school type. So there were a lot of missing values. So in the end, we chose to have one classifier per test version, which means that we have 4 models, so 1 per test version, for 2 different techniques. So that's already 8 models. And to take into account the switching of school type, as I said before, there is a special interest in those who switch. We applied case weights, such that the sum of the group of students that switched is as big as the sum of the group that did not switch, so that they have the same priority. That means we also have for each model 1 without weights, 1 with weights, to evaluate that effect, which comes down to 60 models in total. So to skip right to the model assessment, so here is the IRT performance I showed earlier, and here the well, just for 4 models. So for the test version, model neural network random forest with weights and without weights. So there's only 4 out of 16. You see that the sensitivity and specificity are both higher than for IRT, but that the area under the curve is lower. So it seems to be that for this particular threshold, machine learning performs better, at least for this test version. It's only a sample, but over all thresholds, IRT does better. But we present a more different comparison as well, where we aggregate over all test versions. So we pretend as if the models per test version are actually one model, so we just paste together the predictions, and then calculate the accuracy, and we make this ranking here. And then you see that an unweighted random forest and a weighted random forest both perform the same with an accuracy of 0.81, followed by an unweighted neural network with an accuracy of 0.78, a weighted neural network with an accuracy of 0.73, and finally IRT with an accuracy of 0.69. So what I hypothesized earlier seems to be true here, that a more robust model performs better, at least for all students. But if we zoom in on those students that did switch, so it's only a part of the predictions, then all of a sudden IRT performs better, much better than machine learning. And then indeed a neural network is doing better than a random forest. You can see that the accuracy is much lower here. So you could say that probably the neural network is better at taking into account the unlikely data patterns for those who did switch. And another thing that we see is that the weighted models do better than the unweighted models, which is of course exactly the intention. Whereas in the previous slide you saw that the difference between having weights and having no weights was relatively small. This is actually exactly the same, only small difference here. Whereas here the difference is much larger. So you might say that if you would increase the weights for the group of switches, that probably the accuracy for these models will go up, and for these models it will probably go down. So that leads to the question, how much is the accuracy of the group of switches allowed to increase for the trade-off of the group of non-switches to decrease? So in the beginning, I asked this question, how can educational tests be used to predict school advice? And I gave some domain-agnostic and domain-specific methods. Domain-agnostic, those who are not traditional to the field, so machine learning and domain-specific item response theory. So in general, machine learning performed better for all students. But when zooming in on this group of switches, IRT clearly performed better. And another conclusion was that case weights substantially improve the models. But that is all to take when taking into account that there's another difference with the models, namely in their explainability. Of course, maybe machine learning does better, but is it worth it when you take into account how explainable, how transparent these models are? That is much necessary for students because they also want to know why they were given a certain school advice. You need to be able to trace back why things happened the way they happened. So we also present a theoretical explainability evaluation. Theoretical in that we didn't actually evaluate the explainability with students, but only the models themselves. We used a framework laid out by Lipton, who defined 3 different concepts to doing this. So first of all, the simulatability, which is the extent that a model can be fully understood by a human in a reasonable amount of time. Secondly, the decomposability, which is the extent that each input, parameter and calculation can be intuitively explained. And thirdly, the algorithmic transparency, which is about giving about which mathematical guarantees a model can give, and this is intrinsic to the learning algorithm, whereas the other 2 are not. So starting with the simulatability, so the reasonable amount of time. For IRT, we can say that this is very good because it's a very intuitive model, because the sum score is a sufficient statistic for the whole model. So the higher your score, the higher your ability will be, and thus the higher your school type. For a random forest, you can't really calculate it by hand, that would be too much work, but you can walk through the forest route to leaf for each tree. It's a lot of work, but it's interpretable if you visualize it. And for a network, it's not feasible to calculate it by hand due to the back propagation. And also it's not very easy to understand because of the hidden layer, which doesn't have any real world value. For the decomposability, so about to what extent each input parameter and calculation can be intuitively explained. For item response theory, again, very good, because the difficulty parameter is simply the difficulty of a question on the test, which is something that students can really wrap their head around. And again, the ability can be fully accounted for by the sum score. So both have real world value and therefore easy to explain, whereas for machine learning, they're less easy to explain or less easy to decompose, but you can do it by looking at the hyperparameters and the feature importance to better understand how these models work. I won't go into the hyperparameters here too much because they also vary a lot from model to model. So if you want to know more about that, I'll happily refer you to our paper. But for the feature importance, so we aggregated these by model, by test version. And then you can see that Dutch language skills, it's a particular content area, it's about grammar. It's clearly the most important in both models for both weighted and unweighted, followed by the vocabulary. And the other content areas are more or less the same. You could say that reading skills are a bit less important, but not much, and also depending on which model. But clearly their language skills and vocabulary are most important in both models. And finally, the algorithmic transparency, which is about the mathematical guarantees a model can give. So how well would this model do with a whole different data set? For item response theory, we can say that the item response function is an increasingly monotone function. So the higher the sum score, the higher the ability. But for machine learning, we really can't give any guarantees. A different data set is likely to lead to a very different model. So in terms of algorithmic transparency, the only thing maybe for random forest is that we know that it segmentates vector space, but that doesn't help. So another some more points that I would like to make is that the models are not ready to be implemented into practice, in the sense that this was more of an this study was more of an investigative nature to explore how well the classic approach of IRT performs against machine learning. Another thing is that more data is needed. We did have quite a substantial amount of data, but if you split it by test version and by measurement moments, then in the end, you really don't have so much data. In the paper, you will see that we had to dismiss one test version because there weren't enough switches. So this is also likely to have implications for machine learning. They will probably do better given more data. But for item response theory, it most likely won't have too many implications since it's more of a robust model. So we had to dismiss one test version. That is because there was a mismatch between test version and classes, school types. That is something we didn't take into account the first time, so that's a lesson that we learned, but it's also a choice that we made because we wanted to stick to really to these three major types, since there is a clear distinction within the schools themselves. They're usually usually a school is focused on one school type, so that is the reason why we chose this these classes. Another problem with these models, if they would be implemented into practice, is concept drift. So in the sense that if this model would give a prediction for a student, and the student would, for example, it would say that a student would need to switch school type, and the student would do so. And then 3 years later, the model will evaluate whether the student switched, and they did switch. But the only reason they switch is because the model told them to switch. So there is a positive feedback loop. That's something that has to be taken into account if this ever would be implemented into practice or some future version. And there are also various ethical and legal considerations. Of course, ethical in the sense that would students want to be judged by a model that is fairly intransparent? Because right now, a lot of the advice hinges on the teacher, not on the model. And of course, if the model would be less transparent, it would become more of an issue. And legal considerations in the sense of the GDPR, which states the right to an explanation. When there is an algorithm used, as we've just shown, there isn't always a clear explanation to be given for these machine learning models. All right, thank you so much for your attention.